Good afternoon, everyone. My name is Catalina Sea, and I work at the USS Geodetic Center and Processing Analysis at the University of Santiago de Chile. And I'm presenting today time-dependent GNSS reference frames in tectonically active regions, the Adela approach within Sirgas. The structure of this presentation: first, I will talk about the motivation and the problem. I will give the Sirgas context. I will explain what the Adela model is. I will show its results and how we can apply this model in Sirgas. In seismically active regions, such as the western border of the Americas, as you can see on the map, the Earth's crust is always moving, and this affects the long-term stability of geodetic reference frames. When a big earthquake happens, seismic displacements can move a station several meters, and post-seismic deformation can last from months to years. All of these deformations generate nonlinear surface displacements, then can move a whole network and affect medium to long-term coordinate coherence. In regions like Chile, there is an irregular spatial distribution of networks, so this can complicate consistent coordinate propagation. All of these effects impact geodetic traceability, serving, and operational GNSS applications, such as mining and infrastructure. So the problem is that static coordinates cannot represent a deforming surface. So in order to preserve geodetic traceability, a coordinate must have an epoch and a time and a deforming model associated. Sirgas provides the regional geodetic reference frames for the Americas. It already gives products such as station coordinates and a linear velocity model called VEMOS. VEMOS represents mean yearly horizontal surface displacements. However, it does not represent coseismic displacements, and it does not describe the post-seismic displacements very well. These linear velocity models need to be complemented with nonlinear time-dependent deformation modeling. So as an example, in the map you can see interseismic velocity and the coseismic displacement for the 8.2 earthquake in northern Chile in 2014. So in order to try to solve this problem, ADELA was created. ADELA stands for Analysis of Deformation Beyond Los Andes, and it is a time-dependent reference frames approach designed to operate within Sirgas. ADELA can complement it by adding the nonlinear component. So the basic idea is to model GNSS data using a linear trend, which shows the velocity of the station, a seasonal component that describes the annual and semi-annual signals, an offset that can represent earthquakes or equipment changes, and a transient trend that can represent post-seismic deformation. Here you can see the decomposition of a time series from a station in Argentina that has 2 earthquakes in it. So ADELA started as a research initiative of the University of Santiago de Chile, and it has been funded by the Ministry of Science and the Ministry of Mining. It started as a deformation model with a focus on high-precision applications in Chilean mining, and it has since evolved into a structured workflow that supports kinematic reference frames where it could be needed, like is the Sirgas region. This is operational core of ADELA. It starts with data acquisition. First, the data is downloaded and passed through a quality control check. Then this data is processed to generate time series, which goes into the deformation modeling. In this stage, geodetic products are generated, such as time-dependent coordinates, temporal traceability, the deformation models, and user tools like the ADELA webpage calculator, which I will show later. An important feature of this workflow is the two-stage processing for events of a higher magnitude than 6. First, a preliminary solution is created using rapid IGS products. This is to quantify displacements and evaluate the reference frame deformation. Then a final product solution is created. This is what goes into the deformation modeling. Here is a video of how the Adela web page works. This is the epoch change tool. You can pick the date of the measurement that you have, and then you choose whatever epoch you want your data in. You can also choose if you want a station of reference or if you want to interpolate the data using all the stations. So Adela has been tested in two networks. The first one is Red Geomin, which is the network for Chile. It is the black dots in the map. And also it has been tested at the Sirgascon network, which are the red dots. So in cores, we always have data. So position accuracy reaches the millimeter level. But in server max, the situation is more challenging because we don't always have continuous observations. So accuracy depends on GNSS station density, the solution of the frequency, and the interpolation strategy. We use TPS. Cross-validation tests show that Adela improves reference frame stability from the centimeter level to the millimeter level. Red Geomin is the Chilean implementation of Adela. It is a densification of the Sirgascon network and it's used for high-precision mining applications here in Chile. It provides the operational environment to validate Adela products in Chile. Chile is the perfect lab to do this because it is a highly seismic country and we also have a strong mining industry. Adela enables epoch updates beyond continuous stations through interpolation, and this supports survey marks and users working outside of the GNSS station areas. So Adela within Sirgas. Adela is currently operation in a beta version for the Sirgas region. Actually, the video that I showed you is from the Sirgas model. Its main objective is to maintain consistency with ITRF, IGS, and Sirgascon because kinematic reference frames need to be standardized and compatible with existing geodetic structures. So Adela gives standardized metadata and catalogs to support this, to support reproducibility and transparency. Its products are designed for integration with GNSS software and spatial data infrastructure, and this approach provides a reproducible model for implementing operational kinematic reference frames in the forming regions. In the Instagram, you can see that the residuals are very close to zero, which means that the model fits the observations very well as with the Red Geomin network. So to conclude, operational kinematic reference frames for the forming regions, we have explained that tectonic deformation challenges the stability of static reference frames. So in seismic regions, coordinates need to be time-dependent. So Adela implements this time-dependent approach within Sirgas, and it can complement VEMO's existing velocity models by incorporating the nonlinear component. The Chilean approach shows the feasibility of this approach in Chile in an operational context. And overall, Adela provides a reproducible workflow and a continental roadmap for the transition towards kinematic reference frames. So this is a glimpse of what's coming for us next. We have applied Adela in the Iberian region. This is just preliminary results. We do not want to show final results. This is just to show that Adela can be implemented wherever kinematic reference frames might be needed. That's all. Thank you for the time and attention.